Above your head, the sky looks empty. It looks like a clean, quiet black. But that is only because your eyes were built for clouds and sunsets, not for orbits. If you could see what space agencies see, you would not call it empty. You would call it crowded. There's a highway wrapped around Earth, not one road, but many, stacked like invisible lanes. Weather satellites glide in wide arcs. Communication satellites hold their positions like steady lanterns. Navigation satellites keep time for the modern world, the invisible heartbeat behind phones, maps, shipping, banking, and emergency services. And between them all, moving faster than anything you have ever experienced, is something else. Debris, fragments, shards, screws, paint flakes, dead satellites that never truly died. A piece of metal the size of a fingernail does not sound dramatic. In your hand, it is nothing. In orbit, it becomes a bullet you cannot hear. It travels at around 8 kilometers per second. At that speed, the difference between small and large begins to disappear. The energy comes from the velocity, not the size. The sky becomes a place where even dust can hit like a hammer. This is the uncomfortable truth of the space age. We did not just put machines above Earth. We put our daily life up there. We put our prediction of storms up there. We put our ability to navigate oceans and deserts up there. We put our timing signals up there, the ones that let computers agree on the same second. We turned orbit into infrastructure, and then, quietly, we started leaving trash behind. Most of the time, nothing happens. That is why it feels safe. The satellites keep working. The maps keep updating. The weather forecast appears on your screen like magic. The night sky stays calm. It is easy to believe that space is far away and mostly irrelevant. But the risk we are talking about does not announce itself with a flash you can see from your backyard. It announces itself as a chain reaction. A slow, cold domino line that begins with one impact and ends with a sky that is no longer usable. Imagine a single collision, no drama, no sound, no warning for anyone on the ground. A dead satellite, forgotten, drifting. A fragment, perhaps from an older breakup, crossing its path at an angle that will never happen again in exactly the same way. They meet for a fraction of a second. And then they are not two objects anymore. They are a cloud. When two satellites collide at orbital speed, they do not just crack, they shred. They turn into thousands of fragments, then tens of thousands, then more. Every fragment becomes a new projectile, each one with its own orbit, its own timing, its own chance to meet another satellite later. A single collision is not one event. It is a generator. Now, imagine those fragments spreading into the same altitude where other satellites live. A weather satellite does not have to be unlucky for long. A navigation satellite does not need a direct hit from a full satellite. It only needs a small piece, moving fast enough to pierce a panel, break a radiator, shatter a sensor, or knock a spacecraft into a spin it cannot recover from. And when that satellite breaks, it makes more fragments. The cloud grows, the number of potential collisions rises, the sky becomes more hostile, not because the universe changed, but because we changed the environment around Earth. This is the idea known as the Kessler syndrome. It is the fear that orbit can become so full of debris that collisions create more debris faster than the debris can naturally fall back into the atmosphere. The fear is not a single disaster. The fear is a self-sustaining problem, a feedback loop, a trap. People often imagine the end of something as a wall you reach. But this end is different. This end is a gradual closing of a door. Not all at once, but piece by piece, lane by lane, altitude by altitude, until launching becomes risky. Satellites become short-lived, and the services we treat as normal begin to fail more often. And the scariest part is that you would not feel it at first. At first, it would look like small glitches. A satellite goes silent, another one stops responding, a weather map updates slower, a few GPS readings drift, a flight route changes, a shipping delay becomes normal. The world shrugs. Because the world always shrugs at invisible problems, but the sky does not shrug. The sky keeps moving. Orbit is unforgiving because it is clean and fast. There is no friction to slow things down quickly. There is no gentle breeze to push debris aside. If something is up there, it stays up there for a long time, looping the planet again and again, returning like a clock hand that never stops. So when we talk about the edge of the universe, sometimes the edge is not far away. Sometimes the edge is right above us. It is the edge of what we can safely use, the edge of a technology era, the edge of a highway we built without learning how to keep it clean. In this story, we are not chasing aliens or mysteries at the edge of time. We are chasing a quieter question. How fragile is the modern world when so much of it depends on machines that orbit above our heads? Inside a region of space, we are slowly turning into a shooting gallery. Because the moment you understand the speed, you understand the stakes. A bolt is not a bolt anymore. A chip of paint is not paint anymore. A dead satellite is not dead. It is a future cloud waiting to happen. And once you see that, the night sky feels different. Not terrifying, just real, not empty, not infinite, not safe by default. A place that needs rules and discipline and restraint before the price of neglect becomes too high to pay. A fragment in orbit is dangerous for one reason that never shows up in the pretty space photos: speed. Down here, danger is usually about mass. A heavy object hits harder. A small object feels harmless. In orbit, the rules flip. The energy comes from velocity, and orbital velocity is brutal. Satellites and debris do not drift. They race. They circle Earth fast enough to cross a continent in minutes. So when two objects meet, the impact is not like a crash on a highway. It is closer to a high-speed explosion that happens without fire, because there's no oxygen to feed it, only momentum to tear things apart. This is why people compare space debris to bullets. But even that comparison undersells it. A typical rifle bullet is fast on Earth, but orbital fragments can move many times faster, and they often collide at relative speeds that add up. The point is not the exact number. The point is that at hypervelocity, metal does not behave like metal. It behaves like fluid for an instant. It vaporizes, it sprays, it punches through surfaces that would normally stop it, and it creates secondary fragments from the thing it hits. One small hit becomes a burst of shrapnel, not because the object was large, but because the speed makes the physics unforgiving. Imagine a satellite as a fragile house made of thin walls. It has radiators to dump heat. It has solar panels that are wide but delicate. It has wiring harnesses, fuel lines, sensors, mirrors, star trackers, antennas. It is not armored like a tank, because every kilogram costs money to launch and fuel to maneuver. It is optimized to survive radiation, temperature swings, and micrometeoroids. It is not optimized to survive a man-made shooting range. A tiny chip of paint can pit a window. A metal shard can slice a cable. A bolt can punch a hole straight through a radiator panel, and suddenly the spacecraft cannot control its temperature. Too hot, electronics fail. Too cold, batteries degrade. A small puncture can turn into a slow death that looks like a software problem from the ground. And sometimes the failure is instant. A fragment hits a solar array and shatters cells. A fragment hits an attitude control sensor and blinds the spacecraft. A fragment hits a propellant tank or a critical line, and the satellite becomes uncontrollable. And the most dangerous outcome is not that the satellite stops working. The most dangerous outcome is that the satellite breaks into pieces. That is the part most people miss. The first collision does not end the story. It multiplies the characters. Every breakup creates a cloud. That cloud spreads along the orbit like a smear of invisible glass. Some fragments stay near the same altitude. Some get kicked slightly higher. Some get kicked slightly lower. Some tumble and present different cross-sections. Some are large enough to be tracked. Many are too small to track reliably, but still large enough to destroy something on impact. The sky fills with objects that are both hard to see and impossible to negotiate with. They do not care about treaties. They do not care about schedules. They do not care about your satellite insurance. And the worst part is that the collision probability grows nonlinearly. It is not a simple story where one extra object adds one extra risk. When you add objects to the same region, you add potential pairings. Every piece can meet every other piece given enough time. The number of possible collisions grows much faster than the number of objects. That is why debris is not just clutter. It is a compounding hazard. There is also a psychological trap in how this risk feels. The sky looks calm. Most orbits are huge volumes. Most of the time, nothing hits anything. That creates a false sense of safety. But the system is not safe in the way a quiet room is safe. It is safe in the way a casino is quiet between spins. You can sit for an hour and nothing happens, and then one spin changes your entire night. Tracking helps, but tracking is not magic. Ground-based radars and telescopes can follow many objects, especially larger ones, and operators can sometimes maneuver satellites out of the way. But you cannot dodge what you cannot see. Small fragments are the nightmare because they are numerous, hard to predict, and still energetic enough to cripple a spacecraft. Even when a piece is trackable, avoiding it costs fuel. Every avoidance maneuver shortens a satellite's lifespan. It uses the limited propellant budget that also keeps the satellite in its proper orbit and orientation. So even the act of staying safe slowly drains the system. Now, combine that with the modern reality. We are launching more satellites than ever, not just a few large ones, but fleets, constellations, thousands of moving nodes that make the world feel connected. The benefit is real. The risk is also real. Because when you pack a highway, the probability of collisions rises, and when the speed is orbital speed, a collision is not a fender bender. It is fragmentation. This is where the Kessler idea becomes less like science fiction and more like traffic math. If collisions create debris faster than debris can naturally fall and burn up in the atmosphere, then the region becomes self-polluting. It becomes a place where launches are riskier, satellites die younger, and everything becomes more expensive and less reliable. Not because space is hostile by nature, but because we made a narrow band around Earth hostile through accumulation. And here's the line that matters. This is not a hypothetical problem built from imagination. We, compiler for your channel, are not warning about a thing that might happen someday. We are describing a mechanism that has already happened in the real world, more than once, leaving behind clouds that are still up there right now, still crossing paths, still adding risk with every lap around the planet. A cascade does not start with a villain in a control room. It starts with a single bad intersection at orbital speed. In low Earth orbit, objects are not gently drifting past each other. They are crossing paths at closing speeds that can be faster than a rifle bullet by an absurd margin. 10 kilometers per second is not unusual for a head-on geometry. At that speed, even a bolt, even a paint fleck, carries enough energy to punch through metal like it is paper. So when two full-sized objects collide, it is not like a car crash. It is closer to a fragmentation event where the impact energy turns structure into shrapnel, and the shrapnel becomes its own population with its own orbits. That is the core logic of the Kessler scenario. One collision creates many fragments. Those fragments spread out along the original orbit, but they also spread across slightly different altitudes and angles, because every fragment leaves with its own tiny push. Over time, the cloud stretches into a ring that wraps around Earth, and because the fragments are now a new set of fast-moving targets, they increase the probability of the next collision. Not tomorrow, not necessarily next week, but statistically, inevitably, if nothing changes. The hazard grows not because space is getting filled, but because the number of crossing opportunities grows. More objects means more near misses. More near misses means more chances for one miss to fail. The cruel part is that the most dangerous debris is not the big stuff you can see and track easily. The most dangerous debris is the stuff that is large enough to destroy a satellite, but small enough to be difficult to track reliably. A 10-centimeter fragment is catastrophic and usually trackable. A 1-millimeter fragment can still cause damage and is basically untrackable. Between those extremes is a gray zone where uncertainty lives. You can maneuver away from what you know is there. You cannot maneuver away from what you cannot see, and you cannot shield against everything without turning your satellite into a tank that cannot afford to launch. This is why the problem is not only physics, it is economics. Every avoidance maneuver costs fuel, and fuel is lifetime. Every time you dodge, you shorten your mission. Every time you shorten your mission, you raise the price of your service. And if you do not dodge, you gamble a satellite that might cost hundreds of millions. As the environment gets noisier, operators do more avoidance, satellites die earlier, budgets tighten, insurers get nervous, and the threshold for what counts as worth launching starts to climb. That is how an orbit becomes unusable without any dramatic moment where someone declares it closed. There is already a preview of this reality in the history of debris. We have seen what happens when large objects break apart in high traffic regions of low Earth orbit. We have seen how long those fragments can persist when they are created at altitudes where the atmosphere cannot clean up the mess. The point is not to relive a list of past events like a textbook. The point is to notice the pattern. Breakups at the wrong height do not fade away. They become background risk, and background risk becomes the new normal. Once that normal sets in, the sky develops something like weather, but made of probability. Certain altitudes become more dangerous, certain inclinations become more crowded, certain local times become more saturated. Operators begin to behave like sailors reading storm maps. They plan around dense shells. They choose orbits that are slightly less optimal but slightly less risky. They add margin, they add redundancy, they add cost. The orbit starts to feel less like open space and more like a minefield with invisible mines that never stop circling. And here's the part that makes the Kessler idea feel unsettling in a quiet way. It does not require more launches to keep getting worse. If the collision rate is high enough, the system can keep producing debris through collisions among existing objects. The sky can keep breaking itself even if humanity pauses. That is why the word syndrome matters. It is not a single event. It is a self-sustaining condition, a feedback loop where collisions create fragments, fragments create more collisions, and the loop keeps feeding itself until the environment changes. Altitude decides whether that loop can take hold. Down low, drag is a slow but real cleanup crew. Up higher, fragments can stay long enough to keep intersecting new missions for decades or centuries. So the nightmare version of the future is not that all of space becomes unusable. It is that a few extremely useful bands become too expensive and too risky to rely on. Not because space is full, but because those bands become statistically hostile. If you zoom out far enough, it becomes a civilization-level question. We built modern life on invisible infrastructure, on satellites that do timing, navigation, weather, communications, Earth observation, and science. We did not build it with the assumption that the highways above our heads could become rough, expensive, and fragile. Kessler syndrome is the reminder that these highways are physical, and physics does not care about our expectations. The next step is not to panic. The next step is to understand what it would take to bend the trend back in the other direction. Because the trend is not fate. It is policy, engineering, coordination, and time, all forced to live inside the same geometry. A crowded orbit does not feel crowded the way a city feels crowded. You do not look up and see traffic jams. You feel it as messages and probabilities, as alerts that arrive when you are trying to sleep, as a quiet math problem that says two objects will be in the same place at nearly the same time. In many operations rooms, the day can start with a list of conjunction warnings, predicted close approaches, each one with uncertainty wrapped around it like fog. Space is big, but the orbits we actually use are thin shells, and within those shells, the geometry repeats. The same crossing points come back again and again, because everything is falling around Earth in the same gravitational rhythm. The strange part is that even when you can track an object, you do not truly know where it is in the way you know where a parked car is. You know a best estimate, and you know an uncertainty region that grows with time. The further you forecast, the wider that uncertainty becomes because tiny forces add up. The upper atmosphere breathes in and out with solar activity. A satellite can present a different cross-section as it tumbles. A fragment can be pushed by sunlight. Even the best tracking turns into a moving prediction that is always slightly behind reality. So an operator is often deciding whether to burn fuel based on a probability, not a certainty. If the probability is low, you might ignore it and conserve fuel. If it is high, you maneuver and shorten the mission. And when the environment gets noisier, the number of alerts grows and the cost of choosing wrong grows with it. This is how an orbital region becomes stressful long before it becomes unusable. The system can drown in decisions, too many alerts, too many objects, too many close passes. A few maneuvers are manageable. Many maneuvers become routine. Routine maneuvers become expensive. Expensive maneuvers become impossible for smaller operators. And then the environment starts selecting for only the richest missions, the ones that can afford extra propellant, extra tracking, extra redundancy. The sky does not close with a locked gate. It prices people out. Mega constellations change the mood of this story in a complicated way. On one hand, active satellites with propulsion can dodge, they can coordinate, they can deorbit deliberately. In principle, a large fleet can be safer than a handful of uncontrolled objects, because the fleet can behave like a school of fish aware of itself and able to steer. But the same scale that makes coordination possible also makes failure inevitable. If you launch thousands of satellites, some fraction will fail. Some will lose attitude control. Some will lose propulsion. Some will become passive targets at exactly the altitudes you were trying to protect. And a passive target is not just a dead device. It is a future fragmentation source waiting for the wrong encounter. At that point, the environment begins to feel like it is balancing on a thin edge between control and cascade. Most passes are safe. Most objects never hit anything. But the system does not need frequent collisions to drift into trouble. It only needs occasional collisions in the wrong band, because each large breakup can inject a long-lived cloud of fragments that multiplies the number of future intersections. The danger compounds quietly, and it compounds in the places we love most, because we love them for the same reason the cascade loves them. They are stable, they are useful, they are persistent. If a fragment is placed there, it does not want to leave. There is also a psychological trap built into the way headlines talk about this. People imagine a sudden apocalypse of debris that wipes out everything overnight. Reality is slower and more bureaucratic, which makes it easier to ignore. The risk grows like interest, not like a fireball. A collision happens somewhere you cannot see. A cloud spreads. Operators do a few more maneuvers. Insurance prices creep up. Mission planners choose different altitudes. Some launches get delayed. The orbit becomes less friendly, not because it is full, but because it is statistically hostile. And the worst part is that the hostility is uneven. One altitude band can be fine, while another becomes a roulette wheel. That unevenness is exactly what makes the problem hard to explain and easy to postpone. If you want to know how close the system is to a true runaway cascade, the honest answer is that it depends on altitude, object populations, and behavior. It depends on how many large objects remain in long-lived orbits without a reliable end-of-life plan. It depends on how many operators are willing to share tracking data and coordinate maneuvers. It depends on how quickly we can reduce the number of uncontrolled bodies that could become the next big fragmentation event. In other words, it depends on choices. Physics sets the rules, but humans choose the inputs, and that is both the frightening part and the hopeful part, because it means the future is not fixed. The cleanest way to stop a cascade is to prevent the first domino from falling. That sounds obvious, but it forces a hard idea into the spotlight. Cleanup is always more expensive than not making the mess. In orbit, cleanup is especially brutal because every piece of debris is moving fast. Every capture is a rendezvous problem, and every rendezvous problem is a fuel and precision problem. So the most powerful tool is not a heroic garbage truck in space. The most powerful tool is policy and design, the boring discipline of making sure satellites do not become long-lived hazards after they are done working. That begins with end-of-life disposal that actually happens, not as a promise, but as a guaranteed behavior, even if the satellite partially fails. It means building in a reliable way to lower orbit so atmospheric drag can take over. It means designing spacecraft so they can passivate, meaning they can vent leftover propellant and discharge stored energy so they do not explode years later and create a surprise cloud. It means making design for demise normal, so hardware burns up safely instead of scattering tougher fragments. It means treating orbit like a place you must leave as clean as you found it, because you will want to come back. But prevention alone does not erase the legacy objects already up there. Some of the highest value targets for risk reduction are the big, dead, heavy things. spent rocket stages, defunct satellites, large bodies that cannot dodge. They are the mass reservoirs that could generate the largest fragment clouds if they are hit. Removing even a small number of those high-risk objects can change the long-term math more than removing thousands of tiny pieces that are impossible to chase. This is where the conversation turns from engineering into strategy. You do not need to vacuum the whole sky. You need to lower the probability of the next major breakup in the wrong altitude band. Active debris removal is often described with flashy images, nets, harpoons, robotic arms, but the underlying idea is simple. Match the orbit of a target, stabilize it or attach to it, add drag or push it into a controlled re-entry path. That is it. But doing that safely, repeatedly, and affordably is not a single invention. It is an industry. And the moment you build an industry that can rendezvous and grab objects in orbit, you also create political anxiety, because the same capability looks like a weapon if someone chooses to use it that way. So even the solutions carry human friction. The physics is the easy part. Trust is the hard part. The other pillar is traffic management, because coordination scales better than heroics. If every operator uses different data, different thresholds, different maneuver conventions, then a crowded orbit becomes chaotic even if everyone is trying to be responsible. A shared framework can reduce false alarms and reduce unnecessary maneuvers. Better data sharing can tighten uncertainties and make decisions clearer. Common standards can prevent two satellites from dodging into each other's path. This is not glamorous, but it is the kind of boring coordination that keeps complex systems from collapsing. And when you zoom out far enough, the story becomes a mirror of every shared resource humans have ever touched. The ocean, the air, the radio spectrum, the climate. Orbit is another commons. Everyone benefits from it. Everyone can damage it. And the bill for damage is paid by everyone, including people who never launched a single satellite. That is why the Kessler problem is not only about collisions, it is about incentives, enforcement, and the awkward truth that physics does not care who is at fault. If the environment degrades, it degrades for all of us. The uncomfortable question is not whether we have ideas to keep low Earth orbit usable. We do. The uncomfortable question is whether we can coordinate fast enough to implement them before one unlucky collision turns a manageable problem into a self-feeding one. Because once the cascade starts accelerating, every solution gets more expensive, every mission gets riskier, and every delay costs more than the last. To understand why an orbital debris cascade can feel slow and sudden at the same time, you have to stop thinking of space as one big empty place. Near Earth, it is layered. Each altitude band behaves like a different kind of ocean current. Some layers naturally clean themselves. Some layers preserve whatever you put there for generations. That difference is everything. Down low, the thin upper atmosphere still exists. It is not the kind of air you can breathe, but it is enough to create drag. And drag is a quiet eraser. The lower you are, the stronger the eraser. Objects gradually lose energy, sink, and burn up. At the altitude of the International Space Station, nature is constantly trying to pull everything down. That is why the station needs periodic boosts. And that is why many small fragments do not last forever in that band. It is a messy region, but it is not a permanent storage shelf. Higher up, the atmosphere fades. Drag becomes a whisper. Orbits that look similar on a screen become very different in lifetime. A dead object up there can remain for decades, sometimes much longer, depending on solar activity and how its shape catches the rarefied air. When the sun is more active, the upper atmosphere puffs up and drag increases and the eraser gets stronger. When the sun is quieter, the atmosphere contracts, drag weakens, and the eraser goes half asleep. This is one reason the environment can feel unpredictable, even when nothing new happens. The background physics changes with the sun, and the sun does not care about our launch schedules. Now add the fact that the most valuable orbits are valuable for the same reason they are vulnerable. Operators love certain bands because they are stable and useful. Sun-synchronous paths make imaging and weather observation easier because lighting conditions repeat. Certain altitudes are perfect for low-latency communication constellations. Some inclinations are popular because they cover more of the planet. So the traffic is not evenly spread. It concentrates into highways, and those highways cross each other at predictable points. A close approach alert is basically a warning that two highways are about to overlap at the same time. The scary part is not that a collision is likely every day. The scary part is that the system creates many chances for bad luck, and bad luck only needs to win occasionally. In low Earth orbit, relative speeds during a collision are typically several kilometers per second. That is fast enough that even a small object carries enormous kinetic energy. The difference between nothing happened and thousands of new fragments can be one unseen piece the size of a bolt. This is why the problem is not only about the number of objects, but about the mass and the altitude of the objects. A collision between two small satellites can be bad. A collision that involves a large dead rocket stage can be catastrophic because it injects a huge population of fragments into a long-lived band. And those fragments do not stay politely in one place. They spread along the orbit, they precess, they drift in altitude and orientation, and they turn one collision into a persistent field of hazards that intersects with other orbits again and again. When people talk about the Kessler idea, the most important concept is feedback. One breakup increases the number of fragments. More fragments increase the probability of future collisions. Future collisions create more fragments still. You do not need every object to collide. You need enough collisions in the wrong place to push the system into a regime where it can sustain itself without additional launches. That is the nightmare version. A self-feeding debris environment that continues to produce new hazards even if everyone on Earth suddenly became responsible tomorrow. But even before you reach that nightmare, there's a softer failure mode that is already painful. The environment becomes expensive. It becomes schedule breaking. It becomes a constant tax on missions. Conjunction alerts multiply. Maneuvers become more frequent. Fuel margins shrink. Small operators cannot afford the risk, and they leave. The orbit does not become impossible. It becomes unfair. It turns into a club where only the biggest budgets can play safely. So the real question is not, will low Earth orbit suddenly become unusable overnight? The real question is, which layers are becoming statistically hostile, and how quickly are we making them worse? Because that is how a usable sky slowly becomes a sky that punishes you for being there. Two moments taught the modern space world what fragmentation really means, because they turned theory into a long-lived debris population that could be tracked, modeled, and feared. The first was a deliberate destruction of a satellite in the late 2000s, which produced a huge cloud of fragments and instantly changed the density of certain orbital bands. The second was an accidental collision between two satellites not long after, which proved that you do not need intent to create a disaster. You only need a bad intersection at the wrong speed. These events did not make the sky look different to your eyes. They made the sky different to your equations. After a major breakup, a new kind of background appears, a persistent probability field. Thousands of fragments spread around Earth, each one too small to negotiate, too fast to avoid if you never see it, and too numerous to treat like individual enemies. You can track many of the larger pieces, but that is only the visible portion. The smaller fragments are the cruel part. They are the ones that can punch holes, crack panels, and damage systems without ever being identified afterward. This is where the gap between "we know it is up there" and "we can do something about it" becomes painfully obvious. Tracking is not the same as control. You can predict some conjunctions, but the uncertainty region always exists. It is a cloud around an estimated path, and operators are often deciding whether to burn fuel based on probabilities, not certainties. If you maneuver too often, you shorten your satellite's life. If you maneuver too rarely, you roll dice with an environment that is getting noisier. Mega constellations add a strange twist. In one sense, an active satellite with propulsion is safer than a dead object. It can receive warnings, compute a plan, and move out of the way. When a fleet is well managed, it can coordinate internally and reduce risk. But scale changes everything. Thousands of satellites mean thousands of chances for failure. Some fraction will lose propulsion. Some will lose attitude control. Some will go silent. And every silent satellite becomes a passive target in the very altitude band where the traffic is thickest. The next uncomfortable layer is that collision avoidance is not a perfect safety net. If two operators do not share the same data, they may calculate different risks for the same conjunction. If both try to maneuver without coordination, you can create a situation where two avoidance decisions steer objects toward the same region. In a crowded environment, the problem is not just avoiding one object. It is avoiding everyone who is also trying to avoid everyone else. This is why traffic management is not a luxury. It is the difference between a system that scales and a system that collapses under its own coordination burden. Shared standards for conjunction warnings, shared expectations for how and when to maneuver, and better data sharing can reduce unnecessary burns and reduce dangerous misunderstandings. None of that sounds cinematic, but it is the invisible scaffolding that keeps complex systems from turning into chaos. And then there's the hardest truth, the one that feels like a bill coming due. Even if every new satellite were designed responsibly, the legacy population still exists. Large dead objects in long-lived orbits remain the biggest risk multipliers because they are the mass reservoirs that could produce the next huge fragment cloud. Removing a few high-risk bodies can change the long-term risk more than removing countless tiny pieces, because tiny pieces are symptoms. The big bodies are potential sources. Active debris removal sounds like science fiction until you say it plainly. You rendezvous with a dead object, you attach to it or stabilize it. You change its orbit so it re-enters safely, or you increase its drag so the atmosphere does the work. The concept is simple. The execution is brutally hard and politically sensitive, because anything that can rendezvous with and capture an object in orbit can also be viewed as a hostile capability. So the solution is tangled in trust, not just engineering. That is the real shape of the problem. Physics is not waiting to punish us out of spite. Physics is simply keeping score. Every fragmentation event is interest added to a debt. Every uncontrolled object is a potential future payment. The path away from a cascade is not one heroic mission. It is a boring, disciplined change in behavior, combined with selective cleanup of the biggest risks. It is choosing over and over to treat orbit as a shared home instead of a free dumping ground. And if that sounds heavy, it should, because the stakes are not abstract. The modern world leans on satellites the way a city leans on electricity. Navigation, timing, communications, weather forecasting, disaster response, science. All of it rides on access to a thin set of orbital lanes. The question is not whether we can keep using them. The question is whether we are willing to pay for cleanliness and coordination now, or whether we will pay far more later after the sky has become noisier than our decision-making can handle. If the debris environment ever tips from managed risk into self-feeding risk, it will not feel like an apocalypse. It will feel like bureaucracy getting uglier, faster. More warnings, more maneuvers, more aborted launches, more satellites that quietly run out of fuel early because they spent their lifetime dodging things no one can see. A cascade does not begin with the sky turning white. It begins with operators waking up to an inbox that never stops screaming. The first thing that changes is cadence. Today, collision avoidance is already a routine job for many teams. In a worse environment, it becomes the job. When conjunction alerts multiply, you cannot respond to all of them with careful human debate. You have to automate. Automation helps, but automation also makes the system more tightly coupled. Now, thousands of spacecraft are making fast decisions based on predicted tracks that include uncertainty. That is workable when the environment is moderately noisy. It becomes dangerous when the environment is saturated because small mistakes or mismatches compound. The second thing that changes is access. Launch windows get narrower because you are trying to thread a rocket through a region where debris density is not uniform and not stable. You can plan around cataloged objects, but you cannot plan around centimeter fragments you cannot reliably track. At orbital speeds, a fragment that size is not a pebble, it is a bullet. If the probability of impact climbs high enough, insurers raise costs, regulators tighten requirements, and some missions simply stop being viable. Not because space is closed, but because the economics and risk math break. Then the consequences propagate down to Earth in quiet, annoying ways that people do not instantly link to orbit. GPS timing glitches, communication dropouts, weather models that are slightly worse at predicting extreme storms, shipping routes that lose precision, emergency response that has weaker connectivity at the edges. Most people will not think debris. They will think the internet is being weird. That is how infrastructure fails when it depends on things nobody sees. There is also a scientific loss that feels almost personal. Astronomy does not only depend on one big telescope. It depends on many small ones and on the ability to place instruments in stable, clean orbits for years. A hostile debris layer makes long-lived space observatories harder to operate and more expensive to protect. It also makes the near-Earth environment harder to measure cleanly because every future instrument has to survive inside a more chaotic shell. The most frightening part is how asymmetric the danger becomes. A large, well-funded operator can build redundancy, carry extra fuel, purchase better tracking data, and run 24-hour operations. A university satellite or a small startup cannot. A cascade does not just threaten the technology. It threatens who gets to participate. If the sky becomes a premium resource, access concentrates, and exploration becomes less democratic. And none of this requires a single cinematic trigger. It can emerge from a small number of badly placed events. A collision at the wrong altitude, a breakup involving a massive dead object, a fragment cloud injected into a long-lived highway. The system does not need many shocks. It needs a few shocks that land where nature does not clean up after us. That is what makes the problem feel like a trap. The cleanup mechanisms exist, but only in certain layers. In the worst layers, we are building a museum of our mistakes. So what does fixing it actually mean in physical terms, not in slogans? It means reducing the rate at which we create new long-lived fragments and reducing the number of large, uncontrolled objects that could create the next big fragment clouds. Everything else is supportive, but those are the two levers that change the long-term trajectory. The first lever is prevention, and prevention is mostly engineering discipline. Satellites need reliable end-of-life disposal, not as a nice feature, but as a requirement that is verified like a safety system on an aircraft. That means deorbit capability that still works after partial failures. It means propulsion redundancy. It means power and attitude control designed, so the spacecraft can still execute a final burn even if it is sick. It also means designing satellites to burn up more completely on re-entry, so they do not drop large hazardous pieces back to Earth. A responsible design is not only about space, it is about the full life cycle. The second lever is behavior. Operators need shared rules about how to coordinate avoidance maneuvers and how to share orbit data. Without that, every player is driving with different maps and different clocks. You can be careful and still crash if the other car turns based on a different picture of the road. This is why space traffic management matters, not as a political talking point, but as collision math. A coordinated system reduces unnecessary maneuvers and reduces the chance that two avoidance actions accidentally converge. The third lever is targeted removal. You cannot vacuum the sky. The number of small fragments is too large, but you can remove the biggest risk multipliers, the massive dead object sitting in long-lived orbits. Taking a few of those out of the environment removes future sources of huge fragment clouds. It is like fire prevention. You do not have to extinguish every ember. You remove the piles of dry fuel that would turn a spark into an inferno. Then is where the hard reality shows up again. The technology to rendezvous and capture objects is dual use. It can be used to clean, and it can be used to interfere. So the path forward is not only technical. It is trust-building, transparency, and verification. It is making cleanup normal and visible enough that it becomes boring, because boring is what stable systems feel like. There is also a future where the solution is not only removal, but servicing. Refuel a satellite instead of replacing it, repair instead of abandon, upgrade instead of discard. A healthier orbital economy is one where objects do not become junk by default. That is not sentimental. That is logistics. Every dead satellite is a future hazard. Every extended mission is one less dead object launched into a crowded lane. The optimistic truth is that we still have agency. The environment is not yet a runaway machine. It is a system with inertia, and inertia can be changed if behavior changes fast enough. The pessimistic truth is that space does not forgive laziness. Physics does not negotiate. It only integrates the consequences over time. So the real tension of this story is not whether humanity can keep using orbit. We can. The tension is whether we keep orbit usable for everyone, not just for the players who can afford constant evasive maneuvers and expensive data. Because the moment access becomes rare, the sky stops being a shared frontier and starts being a gated utility. And once that happens, the cost of reversing course is not only money. It is lost opportunity, lost science, and lost resilience in a world that quietly depends on satellites more than most people realize. The first hard truth about orbital debris is that it does not need to be big to be catastrophic. In low Earth orbit, everything is moving so fast that size stops being the main factor. Speed becomes the weapon. Two objects do not bump. They collide with the energy of a high explosive, and then they turn into a cloud of shrapnel that spreads out along the same highways every other satellite depends on. That is why the most dangerous debris is not a dead satellite you can see in a dramatic animation. The most dangerous debris is the part you cannot see. The fragments too small to track reliably. The ones that still carry enough energy to punch through metal and glass, like the vacuum itself is throwing bullets. This is not a hypothetical nightmare. We have already watched it happen in real time. In early 2007, a deliberate anti-satellite test destroyed a weather satellite in orbit and produced a massive debris field. Even years later, fragments from that single event kept showing up in tracking catalogs and collision warnings because the altitude was high enough that the atmosphere could not clean it up quickly. Drag is nature's broom. But drag only works well when you are low enough to feel the thin edge of air. When you are higher, debris can stay up there for years, decades, sometimes longer, circling the planet again and again, waiting to intersect something expensive and fragile. Then came the moment that made the risk feel personal to every operator on Earth. In 2009, a functioning communications satellite and a dead military satellite collided. Not a test, not a controlled event. Two real spacecraft on real missions meeting at orbital speed. The impact shattered both, and the result was a new population of debris spread across busy lanes that were already crowded. What made it terrifying was not just the number of fragments. It was the lesson that modern space is not a clean museum, where each object stays politely in its own exhibit. It is a traffic system. And in a traffic system, a single crash can create chain reactions. That chain reaction is the shadow hanging over every launch today. It has a name: the Kessler syndrome. The idea is simple and brutal. If the density of objects in a given orbital region becomes high enough, then collisions create debris faster than the environment can remove it. That debris increases the probability of more collisions. Those collisions create even more debris. The system moves from manageable risk to runaway risk. It is the difference between occasional storms and a climate shift. It is the difference between driving carefully and realizing the highway itself has become a minefield. One of the most unsettling parts is how the danger hides inside normal operations. A satellite doesn't have to hit a whole satellite. A satellite can be ended by a bolt, a shard, a fragment of a panel, a fleck of metal. At orbital speed, a small object carries huge kinetic energy. That is why spacecraft are built with shielding, redundant systems, and conservative margins. But even that has limits. Shielding is a trade. More protection means more mass. More mass means higher launch costs and lower performance. So every mission lives in a negotiated compromise with physics, and physics does not negotiate back. The only reason this is not already an orbital catastrophe is that tracking has become its own hidden industry. Governments and companies maintain catalogs of objects large enough to reliably track. Operators receive conjunction warnings, estimates of close approaches that might become collisions, and they decide whether to spend fuel to move. Fuel is life for a satellite. Every avoidance maneuver shortens the mission, so the decision is never casual. It is always a bet placed under uncertainty. You are betting that the predicted close pass is real, that the uncertainties are understood, that moving is worth the cost, and that the maneuver itself will not create a different risk later. The public sees a clean image of Earth with a few glowing icons. Operators see probability ellipses and error bars in a sky that keeps getting busier. And then there are events that inject fear into the system all at once. When an anti-satellite test destroys a large object in low Earth orbit, it creates a fresh spray of fragments that spread across orbital planes. The debris cloud does not stay polite. It diffuses, it intersects, it forces operators to run new risk analyses, to perform more maneuvers, to accept more fuel loss, to accept more uncertainty. The quiet consequence is that a single destructive event can impose costs on everyone, not only in one country, not only in one industry, but across every mission that shares the same altitude band. The terrifying part is that the most important collisions are often invisible to the public eye until weeks later, when the numbers show up in warnings and the catalogs expand and the probability curves shift. Space is silent. There is no sound when metal hits metal up there. There is only the aftermath, a slow spread of fragments and a growing statistical weight. It is a disaster that behaves like a rumor. It does not explode in one moment for everyone to witness. It leaks into the system and changes the math. If you want the most honest measure of how real this is, do not look at dramatic images. Look at behavior. Operators move satellites more often now than they used to. They plan missions around collision risk. They choose altitudes with cleanup in mind. They coordinate because they have to. The danger is not a story someone invented to make space feel dramatic. The danger is written into daily procedures, into fuel budgets, into mission rules, into the quiet tension of knowing that a single untracked fragment can end a billion-dollar asset in a heartbeat. The universe does not have to be hostile to make space fragile. Orbital debris is not cosmic evil. It is a bookkeeping problem created by speed, density, and human activity. And bookkeeping problems can become existential when the system they live inside becomes crowded enough. The scary part is not that we do not know what is happening. The scary part is that we do know, and we are still adding more objects to the lanes where the risk is already rising. To understand why this problem is getting harder, you have to picture Earth's orbits not as one place, but as layers. Each layer has its own physics, its own traffic patterns, and its own rules for how long debris survives. People talk about space like it is a single emptiness. In reality, the near-Earth environment is structured, like a city with neighborhoods stacked above one another. Some neighborhoods have constant cleanup. Some neighborhoods keep trash almost forever. The lowest neighborhood is low Earth orbit. This is where many Earth imaging satellites live, where weather satellites take close measurements, where many crewed missions have operated, and where huge constellations now spread across the sky. Low Earth orbit is popular for a reason. It is close. Signals are strong. Latency is low. Images can be sharp. Launch costs are lower than higher orbits. But popularity has a price. It is the most crowded region, and it is also where objects move fast enough that even small mistakes can become permanent scars. Low Earth orbit has one advantage that feels like mercy: atmospheric drag. Even though space looks empty, the upper atmosphere extends far above the surface, thin but real. Down low, drag slowly steals orbital energy and pulls objects downward until they re-enter and burn up. That means some debris will not last forever. But drag is not uniform. Solar activity can puff the atmosphere up and increase drag, then later calm down and reduce it. And altitude matters. A few hundred kilometers can be the difference between debris that re-enters within years and debris that stays for decades. There's no single timer. There's a gradient, and operators try to choose altitudes where cleanup is plausible, while still getting the mission performance they want. Go higher and you reach medium Earth orbit, a quieter but still important band. This is where many navigation satellites operate, the systems that make GPS and similar networks possible. Medium Earth orbit is not as crowded as low Earth orbit, but it is not empty, and it is not cleaned quickly by drag. Debris here can linger a long time. The stakes are huge because navigation is infrastructure. It touches shipping, agriculture, aviation, banking, emergency response, and daily life. People rarely think of a timing signal from space as a fragile thing, but it is. This layer is a reminder that the space environment is not only science and exploration. It is utilities. Higher still is geostationary orbit, the ring where a satellite can match Earth's rotation and appear to hover over one longitude. That ring is precious real estate. It is where many communications, weather, and broadcast satellites operate, because one spacecraft can serve a huge region continuously. The physics here are different. Objects move slower relative to one another than in low Earth orbit, but the value of the slots is massive, and the cleanup is almost non-existent. Drag does not help. If something breaks in geostationary orbit, it can remain a hazard for a very long time. This is why operators perform end-of-life maneuvers to move dead satellites into a graveyard orbit, a slightly higher band intended to keep the ring usable. In other words, geostationary orbit already had to invent waste management because it could not rely on nature to do it. Between these layers are special highways that engineers love because they are useful and fear because they are crowded. Sun-synchronous orbits, for example, allow satellites to pass over a location at roughly the same local solar time, making lighting consistent for imaging. Polar orbits enable global coverage because Earth rotates beneath the track. These are powerful tools, and that means they attract traffic. Whenever you hear that a particular orbital plane is busy, what it really means is that many missions want the same geometry at the same time, and geometry is not infinitely divisible. The crucial concept is that debris risk is not evenly spread. It clusters. It clusters in altitude bands that are popular, in inclinations that produce useful coverage, and in regions where past breakups happened. One collision does not fill all of space with danger. It injects danger into specific lanes, and then that danger slowly disperses. That is why a single destructive event at the wrong altitude can matter more than many small events at lower altitudes that are cleaned up quickly. The environment is not only about how much debris exists, it is about where it exists, how long it survives there, and how it intersects with the paths of active spacecraft. This layered structure is also why the just clean it up instinct is harder than it sounds. Cleaning low Earth orbit might be feasible because you can take advantage of drag and design missions that re-enter naturally. Cleaning higher orbits requires deliberate action because nothing falls. In geostationary orbit, cleanup means moving objects to safe zones, actively removing them, or designing satellites to fail safely. In medium Earth orbit, cleanup is difficult because the region is broad and the objects are spread across many planes. And then there's the human layer on top of the physics layer, constellations. When you put thousands of satellites into low Earth orbit, you are not only increasing capability, you're changing the density of traffic. Done responsibly, with disposal plans and active maneuvering, it can be managed. Done carelessly, it can push the system toward that tipping point where collisions create more collisions. The challenge is that responsibility is not a feeling. It is a set of measurable behaviors. How often satellites maneuver, how reliably they deorbit at end of life, how quickly failed spacecraft are removed from active lanes, how transparently operators share tracking data, and how consistently they follow best practices even when it costs money. This is why the orbit you choose is a moral decision as much as an engineering decision. Putting a satellite into a high, long-lived orbit without a clear disposal plan is like leaving a broken car in the middle of a highway and walking away. The car does not explode immediately, it just sits there. But eventually, someone hits it, and because the highway is shared, everyone pays. The near-Earth environment is not infinite. It only looks infinite from the ground because the distances are huge compared to human scale. In practice, the useful layers are narrow and precious. They are the thin, structured zones where humans have learned to live above the atmosphere. The more we use them, the more the rules of traffic and waste management become unavoidable. In the long run, the real question is not whether we can keep launching. The real question is whether we can keep the lanes usable while we do. The warning does not arrive with a boom. It arrives as a message on a screen, a quiet line of text that says two objects will share nearly the same place in the same moment, moving so fast that the difference between a near miss and a catastrophe can be smaller than the uncertainty in the math. This is the part most people never see. Space looks clean from the ground. Even in the best animations, debris looks like a thin, glittering halo. But for the people who operate satellites, space is a constant stream of conjunction alerts, probability updates, and decisions that feel like steering through fog at highway speed. The system works because we measure, predict, and move. It fails when measurement is incomplete, prediction is uncertain, and movement is impossible. Radar and optical telescopes track what they can, building catalogs of objects that are large enough to detect reliably. Then, models propagate those orbits forward, accounting for atmospheric drag, solar activity, and tiny perturbations that accumulate over time. But this is not a perfect clockwork. Every orbit is a prediction with error bars, and error bars are where anxiety lives. The most brutal truth is that you cannot maneuver away from what you cannot see. A small fragment might not be tracked, and yet it can still end a mission. Meanwhile, the larger tracked objects create their own form of danger because they force decisions. When an alert says a close approach is possible, an operator has to decide whether to burn fuel to avoid it. Burn too often and you shorten the mission. Burn too little and you gamble with the entire spacecraft. And because these decisions happen across thousands of satellites operated by different organizations, the environment becomes a crowded room where everyone is trying not to bump anyone else, while also refusing to share all the details of their movement. Some operators publish orbit data openly. Some share only partial information. Some treat it as sensitive. That secrecy does not create risk by itself, but it makes coordination harder, and coordination is the difference between traffic and chaos. The most unsettling part is that the safest choice for one satellite can increase risk for another if the timing is wrong. A maneuver changes in orbit, which changes future conjunctions, which triggers new maneuvers, which consumes fuel, which increases the number of dead objects later if disposal fails. Even the act of avoiding collisions has a cost that compounds. There's also a quiet hierarchy of vulnerability. A satellite with propulsion can dodge. A satellite without propulsion cannot. A dead satellite cannot. A spent rocket body cannot. And many of the heaviest objects in low Earth orbit are not nimble spacecraft designed for modern traffic. They are large, inert masses left over from earlier eras, drifting through popular altitude bands. They are the worst kind of hazard because they are both massive and uncontrollable. If one of them is struck, the debris created is not just more fragments. It is a long-lived new population of fragments that spreads across multiple orbital planes. That is the nightmare pattern that makes Kessler syndrome feel real. It is not one collision. It is the way one collision changes the math for everything that comes after. The system becomes a place where operators spend more time dodging than doing the job the satellite was built for. And if you want to understand how close we are to that world, you do not need a dramatic headline. You need a simple observation. Collision avoidance maneuvers have become routine, not heroic. Routine, a normal part of operations, like checking weather before a flight. That is not a sign of panic. It is a sign that the environment is no longer empty enough to ignore. What makes this even more surreal is how much of it depends on trust in models. A conjunction alert is not a certainty. It is a probability forecast based on incomplete information. Small errors in tracking can inflate risk or hide it. Atmospheric density changes can shift predicted positions. The geometry of the encounter matters. Timing matters. Even the shape and orientation of objects can matter for drag. And all of that has to be translated into a single decision: move or do not move. That decision is made under time pressure because maneuvers must be planned, validated, and executed within narrow windows. For crewed missions, the stakes are personal. For uncrewed missions, the stakes are still enormous because satellites are infrastructure now, not toys. They carry navigation, timing, communications, weather forecasting, and Earth observation that modern life quietly depends on. The scary part is that you can do everything right and still lose, because space is a shared environment and a chain reaction does not ask permission. The only thing that keeps the system stable is that most objects do not collide most of the time. That sounds reassuring until you realize it is the same logic as saying a crowded highway is safe, because most cars do not crash today. Safety is not a feeling. It is a set of conditions that must be maintained. And in orbit, those conditions are getting harder to maintain every year as traffic increases. If this were only a story about danger, it would end in despair. But space is not a horror movie. It is an engineering problem with a deadline that keeps moving closer. And the solution is not one magical technology. The solution is a stack of behaviors, incentives, and tools that together can keep the lanes usable. The first layer is prevention. The cleanest debris is the debris you never create. That means designing satellites to avoid explosions at end of life, passivating leftover fuel, preventing batteries from rupturing, and making sure that failure modes do not turn into fragmentation events. It means choosing orbits with disposal in mind, not just performance. It means building satellites with reliable deorbit plans so that when a mission ends, the spacecraft does not become a long-term hazard. This is why you see more designs that include drag sails, devices that increase atmospheric drag so dead satellites fall faster. It is why electric propulsion and small thrusters matter, not only for mission performance, but for responsibility. A satellite that can maneuver and then deorbit is not just useful, it is civilized. The second layer is coordination. Space needs traffic rules that can scale, not vague guidelines that look nice in a report, but norms that become default behavior because it is cheaper to comply than to ignore. That includes standardized data sharing for conjunction assessment, clearer protocols for who moves when, and ways to reduce the secrecy that turns coordination into guesswork. Some of this can be automated. Some of it must be policy. The point is that the environment is now too crowded to rely on informal courtesy. Courtesy does not scale. Rules do. The third layer is tracking. The more objects we can track and characterize, the smaller the fog becomes. Better radar, better telescopes, better orbit determination, and better models of atmospheric drag all turn uncertainty into knowledge. And knowledge is the only thing that makes avoidance decisions rational instead of superstitious. When operators can trust the numbers, they maneuver less often, waste less fuel, and reduce secondary risk. When they cannot trust the numbers, they either maneuver constantly or they stop maneuvering until it is too late. Then comes the layer that sounds like science fiction but is becoming unavoidable. Active debris removal. This is the idea that we will send spacecraft to grapple, dock with, or otherwise push dead objects out of busy lanes. The logic is brutally simple. If the most dangerous objects are massive and uncontrollable, then removing a small number of those objects can reduce the probability of the worst chain reactions. But the moment you say it out loud, you run into the real barrier. And it is not physics. It is law and trust. Who owns a dead satellite? Who has the right to touch it? Who is liable if something goes wrong? How do you prove a removal mission is not a disguised weapon? The same technology that can remove debris can also disable functioning spacecraft. That dual-use reality makes everything politically sensitive. So the future of debris removal is not only about grappling arms and rendezvous algorithms, it is about agreements, verification, and incentives that allow cleanup to happen without turning space into a suspicion battlefield. There is also a more subtle solution that might matter just as much as removal: servicing and life extension. If you can refuel a satellite, repair it, or move it to a safer orbit at end of life, you reduce the number of dead objects created in the first place. A healthy spacecraft can also be steered into disposal more reliably than a dead one. Think of it as preventive medicine for orbit. It is less glamorous than a dramatic cleanup mission, but it changes the long-term math. And long-term math is what decides whether the environment stays usable. Because the real enemy here is not one collision. The enemy is the slow accumulation of objects that cannot be controlled, the slow rise in density that turns rare accidents into inevitable ones. This is the moment where the story becomes personal for everyone on Earth, even people who never think about space. The question is not whether we will keep launching, we will. The question is whether we will launch responsibly enough that the orbits we rely on stay open for the next generation. Space is not a frontier you conquer once. It is an environment you maintain. If you treat it like a dump, it will behave like one. If you treat it like infrastructure, it can remain stable. The choice is visible in engineering decisions, in end-of-life compliance, in data sharing, and in whether cleanup becomes normal instead of exceptional. The future is not decided by one heroic mission. It is decided by thousands of quiet decisions made by operators, regulators, and builders who understand that the most valuable thing in orbit is not any single satellite. It is the fact that the highway itself still works. The resin engineers fear a cascade is not because they love doom. It is because orbital speed turns small mistakes into high-energy events. In low Earth orbit, objects are not drifting past each other like slow boats. They are crossing paths at several kilometers per second, fast enough that a bolt, a paint chip, or a shard no bigger than a fingernail can punch through metal like it was paper. That is why this size distribution matters so much. Big debris is dangerous because it can create more debris. Small debris is dangerous because it is hard to track and still has enough energy to damage critical systems. The nightmare scenario is when those two dangers connect, when a single high-mass collision creates a cloud of fragments that spreads across multiple lanes, and then those fragments begin to hit other large objects, and the population of debris grows faster than the atmosphere can clean it up. That is the feedback loop, not one accident, but an environment that becomes increasingly hostile to anything you try to keep alive up there. People often imagine that if a cascade began, it would look like fireworks in the sky. It would not. From the ground, the night might look exactly the same. The violence would be real, but it would be silent and hidden at altitude, detected first as a spike in warning alerts and a sudden surge of tracking tasks. Operators would watch the probability numbers climb. Insurance teams would watch risk models explode. Mission planners would start canceling launches because the window that was safe last month is not safe anymore. The first visible effects would happen on screens, not in the sky. Satellites would begin to maneuver more often, which means they would burn fuel faster, which means their lifetimes would shorten, which means the replacement cadence would accelerate, which means traffic would increase, which means the environment would get even more crowded. The cascade does not have to be total to be devastating. It can begin as a slow grind where the cost of operating in orbit rises year by year, until only the richest, most hardened systems can survive. And even they have to spend more of their life dodging than doing their job. This is why mitigation is not optional, and it is why timing matters. Debris removal, disposal compliance, and better tracking all help, but they help most when the environment is still within a stable range. Once the density crosses certain thresholds, every additional piece of debris creates more risk than the previous one, because it increases the number of potential pairings. Risk scales in a way that feels unfair. Double the objects, and you can more than double the conjunctions because each object has more possible encounters. That is why the early years of congestion can feel manageable, right up until they do not. The system can look stable while it is quietly loading tension, like a forest that feels normal until the day the weather turns and a single spark changes everything. There is a deeper reason the debris problem is so psychologically difficult. It is a tragedy of shared space. The benefits of launching are immediate and individual. The cost of leaving objects behind is delayed and collective. A company gets paid today for a satellite that works today. The harm of that satellite failing and becoming uncontrolled shows up years later as risk spread across everyone. That mismatch between short-term reward and long-term cost is how shared environments break, whether it is fisheries, air pollution, or orbital highways. Space is just the newest place where human incentives meet physics, and physics refuses to negotiate. Gravity does not care who owns what. Collisions do not care who meant well. The environment responds only to mass, motion, and density. So when you hear experts argue about orbital debris, listen to what they are really arguing about. They are not arguing about whether space will become unusable tomorrow. They are arguing about whether we will treat orbital safety like a real infrastructure problem now, while it can still be managed cheaply, or later, when the cost becomes brutal. The uncomfortable truth is that we already know how to reduce risk. We know what disposal practices work. We know what design choices reduce fragmentation. We know that tracking must improve and that coordination must become routine. The gap is not knowledge. The gap is discipline. The future depends on whether discipline becomes default behavior, because the universe will not forgive sloppiness just because our business models prefer it. If you want to understand what is at stake, imagine waking up to a world where space is still there, but it is less usable. Not because rockets stop working and not because the sky becomes closed, but because the safest lanes become expensive, risky, and crowded, and the margin for error shrinks until every mission carries a new kind of fragility. Navigation satellites do not disappear overnight, but they become harder to replace and harder to maintain. Weather satellites still exist, but gaps appear in coverage when replacements are delayed or launches are rerouted. Communications constellations still deliver service, but their operators spend more fuel and more time avoiding conjunctions, shortening mission life and increasing churn. The infrastructure does not collapse in one dramatic scene. It degrades the way real systems degrade, through delays, outages, higher costs, and less reliability. And then you realize that modern civilization is built on quiet reliability. Timing signals, broadband backhaul, emergency coordination, shipping logistics, aviation routing, storm tracking, wildfire monitoring, crop forecasting, all of it leans on the assumption that space is accessible enough to be refreshed when hardware dies. Debris turns that assumption into a gamble. This is the part where the word edge stops being poetic and becomes literal. There is an edge to what low Earth orbit can safely carry. There is a carrying capacity to the lanes we use most, and when we push past it, the environment begins to punish us by raising the baseline risk. In the best case, that punishment looks like a higher cost of doing business. In the worst case, it looks like a debris cascade, sometimes called the Kessler effect, where collisions create fragments, fragments create more collisions, and the rate of debris creation begins to outpace the rate of natural cleanup. The key idea is not apocalypse. The key idea is that the environment can tip from a regime where accidents are rare into a regime where accidents become statistically inevitable over long enough time. Even if nobody is reckless, when the background becomes dense enough, you do not need villains. You only need time. The strange thing is that the solution requires both humility and ambition at the same time. Humility because we have to admit that orbit is not infinite, and that the absence of a border does not mean the absence of limits. Ambition because keeping orbit usable will require new systems that treat debris like a managed waste stream instead of an invisible afterthought. That means more transparent tracking networks, better standards for sharing orbital data, and clear norms for who maneuvers when. It means engineering satellites to fail gracefully and deorbit reliably. It means making end-of-life disposal as non-negotiable as seatbelts. And eventually, it means proving that active debris removal can be done safely, routinely, and without turning into geopolitical paranoia. None of that is glamorous in the way people imagine space should be, but it is exactly what maturity looks like. The frontier era ends when you stop treating the environment as free and start treating it as precious. There is also a hopeful twist that is easy to miss. The very technologies that create congestion also create capability. We are better at precision navigation than ever. We are better at automated rendezvous. We are better at machine vision and guidance. We are building spacecraft that can dock, refuel, and service. Those tools can either deepen risk or reduce it depending on how they are used. A future where satellites can be serviced and disposed of cleanly is not fantasy. It is a choice. And the reason the choice matters is that space is not only a mirror for human curiosity, it is now a mirror for human responsibility. We are learning in real time whether we can build powerful infrastructure without poisoning the environment it depends on. So the real question is not whether we are approaching the end of space. We are not. The sky is still there. Gravity still holds the lanes open. The question is whether we are approaching the end of careless space, whether the era of throwing hardware upward and forgetting it can continue without consequences. Physics says no. The only path forward is a version of spaceflight that is grown up enough to clean up after itself, coordinated enough to share lanes, and honest enough to accept limits before the limits accept us. That is what makes this story so quietly intense. It is not about an alien threat or a cosmic monster. It is about a human-made edge, the place where our habits meet the hard geometry of orbit, and the universe asks whether we can change before the math forces us to. There is a version of the future where this problem stays annoying, expensive, and manageable, and there's a version where it becomes a wall you keep slamming into. The difference between those futures is not luck. It is policy, engineering, and coordination, applied early enough that the environment never crosses the point where collisions become self-feeding. The first layer is the least dramatic and the most effective, preventing new junk. That means designing satellites and upper stages so they do not explode, shed parts, or break into clouds when they fail. It means making passivation and safe end-of-life behavior standard, not optional. It means planning deorbit or graveyard disposal the same way you plan power budgets and thermal control as a core requirement. In orbit, later is not a time. It is a risk multiplier. The second layer is traffic rules that work even when nobody is friends. Space is global, but operators are fragmented, and every operator has a different incentive. So the rules have to be boring, clear, and easy to follow. Who moves first in a predicted conjunction? How quickly you must respond to warnings? What counts as responsible disposal? What data you share, and how you share it? The most important thing is not a perfect rulebook. It is consistency. The system becomes safer when operators can predict each other's behavior. A world where everyone follows a simple playbook beats a world where a few teams have brilliant practices and everyone else improvises. The third layer is visibility. You cannot manage what you cannot see. Tracking has improved massively, but the hard part is not just detection. It is identification, precision, and speed. A warning that arrives too late is not a warning. It is a post-mortem. Better sensors help, but so does better modeling, better fusion of data from multiple networks, and better reporting between operators. And there is a psychological trap here. Because space looks empty, people underestimate how many near misses are happening. Most of the work is hidden. Thousands of conjunction assessments, constant filtering, tiny updates in predicted orbits. The system is already a live air traffic problem, except the vehicles are moving faster, the lanes are wider, and the consequences of collisions last longer. Then there is the step that makes everyone uncomfortable. Cleanup. Not metaphors, actual removal. The reason this is sensitive is obvious. Anything that can rendezvous with a dead object can also rendezvous with a living one. Anything that can push an object out of orbit can also push it somewhere else. So active debris removal lives in a shadow zone where safety and security overlap. But the physics does not care about our discomfort. Large abandoned rocket bodies and dead satellites are the highest mass collision risks. Removing a small number of the most dangerous objects can reduce long-term risk more than chasing countless tiny fragments. The idea is not to vacuum the entire sky. The idea is targeted risk reduction, like removing the driest brush from a forest before fire season. There are multiple concepts for how to do that without turning orbit into a paranoia contest. Some involve tug-like vehicles that dock and guide objects into controlled re-entry. Some involve attaching a device that increases drag so the atmosphere can do the rest. Some involve servicing, refueling, or moving satellites into safer lanes rather than letting them die in place. What matters is not which concept wins a technology contest. What matters is proving that the practice can be transparent, verifiable, and governed by agreements that reduce fear rather than create it. Trust in orbit is not a vibe. It is a procedure. The hardest part of all is incentives. Space junk is not created by evil people twirling mustaches. It is created by normal operations where the immediate reward is clear and the long-term cost is diffused. So the future depends on whether responsibility becomes cheaper than irresponsibility. That can happen through insurance pricing, licensing requirements, deposit-like mechanisms that reward clean disposal, shared standards that make compliance straightforward, and consequences that are real enough to change behavior. When the economics align, safety scales. When they do not, the environment slowly accumulates debt. And here is the key twist. None of this is only about protecting expensive hardware. It is about protecting time. A stable orbital environment is a time machine for civilization. It gives you continuity. It gives you weather records that stretch across decades. It gives you climate measurements that are comparable year to year. It gives you the ability to respond to disasters with updated images and reliable communication. It gives you the option to do science that requires long baselines and repeat observations. Debris threatens that by turning the sky into a place where everything is shorter-lived, more fragile, and more expensive to replace. It steals the long view. And the long view is where humanity does its best thinking. When people say the edge of space, they usually imagine something out there, a cosmic border you reach by traveling far enough. But the edge we are talking about is closer and stranger. It is the point where a useful environment becomes a hostile one, not because the universe changed, but because we did. Space is not fragile in the romantic sense. Space is brutally indifferent. The fragility belongs to our systems and to our willingness to treat a shared environment like a shared environment. The honest ending is not that we are doomed, and not that everything is fine. The honest ending is that we are early. We are still in the phase where a few decisions can bend the curve. If operators treat disposal as default, if tracking becomes more open and more standardized, if the most dangerous objects are dealt with before they fragment, then low Earth orbit stays usable and the future remains wide. But if congestion continues without discipline, then the math tightens. Not overnight, not in one cinematic disaster, but in a slow narrowing of what is safe, what is insurable, what is affordable, what is reliable. The world does not lose space. The world loses easy space. And that is a quieter kind of loss, because it hides inside budgets, delays, outages, and missed opportunities. There is also a moral clarity to it that is rare in big science stories. This is not a mystery we can only observe. This is a problem we can influence. The sky above us is not a landfill by destiny. It becomes one only if we act like it is. The same human intelligence that built precision rockets and folding mirrors and global constellations is capable of building the boring infrastructure of responsibility. It is capable of rules, compliance, tracking, cleanup, and cooperation. The question is whether we value the future enough to do the boring parts with the same intensity we bring to the spectacular parts. So if you take one idea from this entire journey, let it be this. The end is not a place. The end is a behavior. The boundary is not drawn by physics alone. It is drawn by density, by incentives, by coordination, by whether we treat orbit like a commons or like a free-for-all. The universe is vast, but the lanes we depend on are specific, and their limits are real. The edge of space is not where you think, because it is not a cliff in the darkness. It is a line we can approach without noticing until the consequences make it impossible to ignore. If you want more long-form space documentaries like this, give the video a like and subscribe. It helps this channel reach the people who need calm, deep explanations instead of noise. And tell me in the comments what you want next. Deep space mysteries, black holes, the cosmic horizon, or the next big problem we are quietly creating above our own heads. Until then, keep looking up, but keep thinking like an engineer. The sky is not just wonder. The sky is responsibility.